This is Coding Math, Episode 42, Isometric 3D, Part 2. In the last episode, we saw how to create a grid of tiles, translate grid positions into screen positions, and draw tiles or blocks or render pre-created bitmap tiles from a sprite sheet of isometric tiles. Up to now, we've completely randomized what goes where. First thing we'll look at today is how to create a predefined layout and parse it so that we're drawing specific tiles in specific places. Let's start with drawing colored tiles manually. We'll take up the core code we wound up with last time. This has the basic template plus the draw tile, draw block, and draw image tile functions. We'll need some kind of model that defines the entire grid and tells us what color to draw each tile. Normally you'd probably want to put this in some kind of external XML, JSON, or other text file. But we'll assume you know how to do that, and for the sake of simplicity, I'm just going to code it right into our main script file. A two-dimensional grid is easily created with a two-dimensional array, so we'll go with that. I'll create an array called grid. Each element of that array will be another array filled with the color names. The first row of the array will be the first row of the grid, with y as 0, and x increasing from 0 to 9 in this case. I'll make all of those blue. The second row will be y equals 1. Here I'll make the first and last elements blue and the rest red. And I'll copy and paste that 7 more times. And then put another fully blue row at the end. Finally, I'll make the 4 tiles in the center yellow. Now we have our model in this grid variable. We just need to loop through it and create tiles using the specified color in the draw tile function. This is really basic and shouldn't need a whole lot of explanation. Now there's just a few more steps to do here. Oh, wait. No, there's not. We're done. Here's what our grid looks like. Blue all around the edges, red inside, with a yellow center. Pretty sure that's what we defined. So let's move on to blocks. I'm going to use the same grid here, but use search and replace to change all the blues to 1s, and all the reds to 0s, and finally the yellows to 2s. Then all we need to do is change draw tile to draw block. The syntax is exactly the same. The grid contains z values now. These will get passed into draw block, and the function will draw a block with the specified size. Here we go. Yep, that looks right. There's a bit of ambiguity there with the tops of all the blocks being the same color. I'm sure you can figure out how to get differing colors in there as well, which should solve all of that. Rather than the grid elements just being simple strings or numbers, maybe they could be objects themselves with both height and color values stored in each object. I'll leave that up to you. Finally, we'll try the same thing with a sprite sheet. Now we have 16 different tiles to choose from, and we can simply define the grid by specifying which tile will be in which position. You don't need to see me typing all these integers in, and it takes a bit of work to design a pleasing layout with so many possible tiles. So I've gone ahead and done that behind the scenes already, and now I'll just paste it in here. As you can see, we have mostly high numbers in the top left. These are mountains and rough ground. Then mid-range numbers in the lower left are all grass. And in the middle and upper right are lots of 0s to 3s, which are different shades of water. Now we need to go back and do what we did last time for the image loading. Create an image element, listen for its load event, and then call a draw function. Then set the source of the image. And again, draw will just wrap the for loop that draws the tiles. We can just change the name of the function here from draw block to draw image tile. And that should all work. Let's not forget to change the tile size. And there you have it, a nice little seaside vacation spot. I tried to use a good assortment of tiles here, but there are ones I didn't even touch. Note that the code still had the line in there to lower any water tiles by a few pixels, and you can see that's still in action here. Now so far all we've managed to do is create static landscapes. They're starting to look pretty nice, but I think it's maybe time we start to interact with them. I want to have a character move around in our tile world, and I'll do that by drawing to canvas. But I don't want to have to redraw the entire world every time the character moves. So what I'm going to do here is add another canvas called Character Canvas, right above the first one. You'll note that in the CSS, canvases are absolutely positioned, and align so that their top left corner is at 0. So these two canvases will perfectly overlap. We'll draw the tile world on the bottom one and move our character around in the top one. In the JavaScript, we'll have to duplicate some of the canvas template to get a reference to the character canvas and get its context, which we'll call character context. Then we'll have to size it to full screen along with the original. And finally, we'll need to translate it in the same way we translated the original canvas. And now we need a character to draw. You can use whatever you want. I'm using this silver ball. You might want to use another sprite sheet for your character. This will let you use different frames to show the character facing in different directions, etc. All that's way outside the scope of this video, which is why I'm just using a silver ball. Again, I'll need to create an image element, set a load handler, and set the source. In that handler, I'm going to call a function called drawCharacter, passing in the character image and an XY of 0, 0. I'm also going to listen for a keyDown event and set the handler to a function called moveCharacter. We'll need to create both of these functions. First, drawCharacter. Again, this takes an image, X, and Y. We'll reuse some of the tile drawing codes, saving the context, translating it to calculated screen X and Y, and restoring the context. But remember, we're using the character context now, so I'll change all of those. I'm also going to want to clear the character canvas, so I'll call clearRect on it. Because the context is permanently translated, I have to use -width divided by 2 and -50 to point to the top left corner. The width and height won't change. One thing you might want to look at here is just clearing the portion of the canvas where the character is. You don't need to clear the entire canvas each time. Again, I'll leave that up to you to figure out. Since I copied this translation code over from drawImageTile, it has the water offset in there, so I'll get rid of that. Finally, I can call drawImage, passing in the image. For the position, I'm going to pass in -imagewidth divided by 2 for X. This will center the character on the X point. And I'll use -imageheight as the Y. This will make it so the very bottom of the image is on the point we're drawing it to. Okay, let's see what we have. That's not right. The ball is floating in the air. Now part of what's going on here is the tile set itself. Let's take a look. Note that the top corner of these tiles, which is the 0, 0 point on any given tile, is not at the top of the image. It's actually about 11 pixels down from the top. Now we could make an adjustment of 11 pixels when we draw the character, but it makes more sense, I think, to adjust the tiles so that their top corner is actually at 0, 0. So back in the drawImageTile function, I'll subtract 11 pixels from the Y translation. These kind of micro adjustments are things you'll probably have to do to accommodate any artwork you get. Ideally, it will be consistent across the different graphics, and you can set some kind of property for that, rather than hard-coding a magic number 11 like I did. Anyway, I'm also going to go into that first drawCharacter call and set the Y position to 9 so it's drawing on a grass tile instead of a mountain, as the mountain itself hides that top corner. Run that, and we have this picture. Still looks a bit weird, but it's actually right on. It's right at the origin point of tile 09, which is that top middle corner. We could adjust the character to draw a bit lower, but instead what I'll do is set the position to 0.5, 9.5, which is halfway to the next tile on each axis, putting it in the middle of the tile. And that looks about what we want. Now we can implement that moveCharacter function. First of all, since we're going to be keeping track and moving the character position, we better make some variables to hold that position. I'll make a charx and charY variable and set them to 0.5 and 9.5, which is what we just used. And I'll use those variables instead of the hard-coded values in the first call to draw a character. Now the moveCharacter function. That's going to get an event object. We can run a switch statement on the event's keycode property. The left, up, right, and down keys will have keycodes of 37, 38, 39, and 40 in that order. So I'll make cases for each one of those. The left and right keys will move the character on the x-axis, and the up and down keys will move it on the y-axis. So in the left block, I'll decrement char x and call drawCharacter. In up, I'll decrement char y And in right and down, I'll increment those properties. And that's that. Let's see how it looks. Well, pretty neat. We can move all over the grid. We can even climb mountains and walk on water. And walk right off the edge of the world and keep on going. So maybe we better apply some constraints here. In the left case function, I'll call this function named canMove, passing in char x minus 1 and char y. This is going to return true or false depending on what tile that xy ends up being. If it's true, it means the character can move there and will do so. If it's false, nothing happens. And I'll do the same thing for the up, right, and down blocks, passing in char y minus 1, char x plus 1, and char y plus 1 as their new positions. Now we need to create this magical canMove function. This will do two things. First, it's going to see if we're even on the grid. But to do so, we'll need to be checking array elements. Remember that our char x and char y are now floating point numbers, so we're going to have to turn them into integers. Flooring them will work nicely the way we set it up. 0.5, 9.5 will floor to 0, 9, which is the tile we're actually on. If y is greater than the grid's length or less than 0, we just return false. If we pass that test, then we can get the grid row for the given y. If x is greater than that row's length or less than 0, we again return false. Okay, we made it that far, or at least on the grid. We'll get the tile at xy and see what it is. Remember that the grid is composed of an array of rows first, so we have to pass in grid yx to correctly index the row first and then the column of that row. We know that tiles 0 to 3 are water, so we shouldn't walk on those. And tile 15 is the mountain. All others are okay. So we could say if tile is less than 4 or tile is greater than 14, return false. And if we fall through all of that, we're good. Return true. This could all be rewritten to be more elegant, but this should do the trick for now. And a final check. Well, we can still move, but we can't move off the edges, on the water, or onto any mountains. Perfect. Of course, this is only an example of how you might want to set this up, and a very simple example at that. But however you set it up, these basic principles will apply. We'll do one final episode in the series looking at a few more advanced techniques.